another DaSSWeb, and today we have the pleasure of hosting Dimitris Karlis, a professor in the Department of Statistics at the Athens University of Economics and Business. Dimitris has received his bachelor in statistics from the same university and as well as his PhD. He has published many papers in peer-reviewed statistical journals. His research interests include mixed models, discrete value time series, computational statistics, multivariate count data analysis, statistical modeling for sports data, dependence modeling via copulas, among others. He has been associate editor and editor-in-chief of journals, peer-reviewed journals, and in particular, he was editor of the Biometrics Bulletin of the International Biometrics Society. He has supervised 5 PhD students and more than 100 master theses, and is currently supervising 5 PhD students. He has participated at numerous international conferences, is a member of the American Statistical Association, and the former president of the Eastern Mediterranean region for the International Biometrics Society. He is a member of the Greek Statistical Institute and has participated in European projects, particularly in the field of statistics. Dimitris, thank you for accepting our invitation, and the floor is yours.
My pleasure. So thank you very much for this kind invitation. It is my pleasure to present in your statistics seminar. So today I'm going to talk about multivariate ordinal time series. And this is joint work with my PhD student, Anna Alpadidi. And we're going to present, let's say, the current research on this topic. So to start with, the idea is that we have data which are time series, but actually the observations are from a set of order categories, and such data can occur in many different circumstances. For example, a very typical one when we collect data with questionnaires. So we have the same question, for example, every day, and this way we have a long time series with the answer in the same question. Another very typical example is that in some cases we need, let's say, to discretize continuous time series. This is very typical in in EEG because we don't trust so much the continuous outcomes. That's why we prefer, let's say, to split it in different ranges, and this produces ordinal data. This is also the case in some official statistics because, for example, when we measure unemployment, Eurostat is not very happy with the particular numbers because they know that they may contain a lot of noise depending on the way the data have been collected. That's why they prefer, let's say, to make them ordinal. And of course, any kind of ratings can be of that case. A typical example here, which perhaps can be a kind of motivation from what I'm going to present, is about the following real circumstance that a professional football team collects data every day. There is a very small mobile application and the players receive every day a message in their mobile phone, and they have, let's say, to answer just 2 questions. So actually the idea is that how tough was training yesterday and how do you feel today? So actually this produces time series with ordinal responses. Actually we have 2 time series per player, and actually we have a lot of them. So we have, let's say, data of quite large complexity with a lot of interesting questions there. I have some plots just to motivate the whole thing. So this is, let's say, from a paper from Jan and Weiss about Beijing air quality. So we see for a long time series, it is about, let's say, 6 years, 5.5 actually. And for each day we have, let's say, the air quality. So this is a typical ordinal time series. Another example is this one. So Jennifer every day kept notes about her boyfriend mood, and we have something like that. So for example, around here we have the day that Timmy's team has lost the game, and you see that during, let's say, the other days, there is a lot of ups and downs in his mood. More examples. This is the example that I mentioned about unemployment rate. So here we see 3 different countries, and this is a very interesting, let's say, example, because actually you see very different patterns. So you see, for example, Portugal, you see that the unemployment rate stayed for a long period relatively stable at the top, while if you see, for example, Finland, you see a lot of fluctuation around different states. So this is a kind of issues that we have to take into account when we model ordinal time series. My final example is this one. This is the credit rating of the countries in the European Union. So actually you see that there are countries with very little move, like for example Austria here, and you may see, for example, Greece, that while starting quite high for a very long period, we were at the bottom of Europe, while we are doing a little better right now. So actually, this is a typical example of, let's say, ordinal time series. So having said that, we all know that there is a huge literature on continuous time series, and actually there is quite a lot of different models. There is also an increasing interest on count time series, and I remember one of my first trips in Portugal, in Aveiro. There were very few people working on something like that in 2010. So now, 15 years ago, there is a huge number of papers every year about count time series. What is a little of interest here is that most of the count time series can be seen in 2 different avenues. So the one is based on some kind of thinning, and I will explain you what I mean later on. And while the other is a kind of feedback on parameter or observations, and this will be the basis for creating some ordinal time series in a few minutes. Be aware that the literature on ordinal and categorical time series is much less developed, so there are not so many models. And this is, let's say, to put it this way, a big opportunity for some research in the near future. If we consider many time series together, if we consider multivariate time series, the literature is even more sparse, and there are very, very few papers, and this is what we try to contribute with this work and my talk today. Just a quick glimpse on count time series. So here I have a time series and I observe counts. So actually my random variables xt are taking values in the positive axis and in positive integers and 0. So this is, let's say, one very well-known model that tries to mimic the autoregressive model. What is different is that instead of having, let's say, a multiplication here, we have this operator, which we call the binomial thinning operator. So the idea is that if we multiply the previous value with, let's say, a number, what we obtain is not an integer. So this trick here just makes the whole thing to be integers, so we have a time series on the integers. RT here is a sequence of uncorrelated non-negative integer value random variables. We call them innovations, and this is, let's say, one very popular model, well known in the literature as integer autoregressive model. So in a few slides, I will try to do something similar in the sense that when we try, let's say, to create an ordinal time series, we need this kind of operation, which is called thinning. And to be honest, the thinning can be written this way as well. So the binomial thinning I have used in my inner model is actually a sum of some Bernoulli random variables. So here yt are Bernoulli random variables. If I replace yt with any distribution, I can obtain a huge number of different thinnings and actually a huge number of different models. So one avenue to describe and create such models in a few slides is to consider a similar kind of thinning for the ordinal variables. The second way to create my models will be like that. This is another popular model for counts, which is called the integer guards model. And actually here what we say is that xit, given the past, follows, let's say, a Poisson distribution. This can be any other discrete distribution. And what we have and what gives, let's say, the autocorrelation structure, the temporal structure, is that the current value of the parameter of the current value of the parameter of the distribution depends on the previous values, but also the previous observations. So this is a second way that we can have the model. I may say here that this model and this model are very related. So actually, what is the change here is the way that we impose a mechanism for creating the time series idea. Okay, having said that, I'm coming to the ordinal time series. For the univariate case, we do have models, and actually the easiest way is to consider Markov models with transition matrices, and this can create either hidden Markov models or simple Markov models, and this can create, let's say, time series. We can have models based on the GLM type, so actually we can use previous observations as covariates in a GLM. We can have discrete autoregressive models, and this is something that I'm going to describe in a few slides, because this makes use of a kind of thinning operation. We can also consider, let's say, ordered probit models. So let's say that we have a continuous time series and we split we discretize this continuous time series as we did in the probit models. There is some literature saying that when you have ordinal variables, you can consider this as the number of steps you need from the baseline. So there is some literature saying that you can still use a kind of count time series for ordinal data. There is a combination of uniform and binomial time series models. Cube is a known model for questionnaires and for ordinal data from questionnaires, and we can have, let's say, a time series component there. There are models using ordinal patterns. There are models using the stereotype model, where we can add one autoregressive parameter, so the current parameter depends on the previous values. We can also create models with the conditional copulus. So actually, what I would like to point out here, and I don't say that my list is complete, is that there are several different ways and several different ideas how we can create ordinal time series. But so far, I'm talking only about univariate ordinal series. So I need to go one step further and define bivariate and multivariate time series. So today, what I would like to discuss is the case when we have k ordinal time series, not just one, and we would like to model them jointly. So we care for the autocorrelation of each series, but also for the cross-correlation between the series. So in the example I just have shown about the employment rates, we care about how the employment rates, let's say, go across time, but at the same time point, we would like to have a kind of cross-correlation between the different countries. And my problem is that even if we ignore the temporal aspect, it is not easy to have a simple multivariate distribution for a lot of ordinal variables. And we still want, let's say, to account for autocorrelation and cross-correlation. So actually, we need a little more complicated models. I will start for considering bivariate models. And the main reason for that is that this is going to be the building block for the multivariate models. So at the second part, I'm going to discuss about multivariate models, but the basic idea is to describe the models for a series of bivariate models and using a kind of inference based on what is called pairwise likelihood, we are going to be able to fit the multivariate models as well. Okay, so I will start with a novel model for bivariate time series, which is based on the thinning idea just mentioned. And the idea is that we have two time series, and we want to jointly model them. So actually we need a bivariate model for ordinal time series, and we want to account for both autocorrelation and cross-correlation. What we are going to do here is to extend the discrete autoregressive model to the bivariate case. So I need to define a little what is this discrete autoregressive model in a while. Before doing that, I must say that there are very few bivariate ordinal time series models. We have searched the literature quite a lot, and we have found only 3 papers about that. The first paper uses a latent variable approach. So actually we have a bivariate continuous time series model, and actually we discretize it in order to get the ordinal outcome. So this is one approach. The second approach is that we may start with let's say two independent time series, and using some kind of random effects we make them connected. So actually we introduce a kind of cross-correlation by just using random effects. And a final approach is based on copulas, and somehow we are going to use copulas as well here, that takes, let's say, both the bivariate, the across time and between time points, a correlation by using copulas. So my model will be the discrete autoregressive model of order 1. So this dates back to 1978 from the seminal paper of Jacobs and Lewis. And the idea of discrete autoregressive model is quite simple. What we observe at time t is either what we had at the previous time point with some probability phi, or is a random draw from a distribution. Again, I call them the distribution of innovations with the complementary probability. So actually this is the very, very simple thing. This is known in the literature as the Pegram operator. So the Pegram operator is a mixing operator that just mixes 2 or more variables. So the notation is something like that. So the Pegram operator assumes that x takes the value w1 with probability f1, or w2 with probability f2, or w3 with probability phi3, while the sum of the phi's is 1. So actually it is a mixture model. So this is what the model assumes. In the time series context, what we say for a model of order p is that what we observe at time t is either what we observed the previous time point, yt minus 1, with some probability phi 1, or 2 times before with probability phi 2, and so on. Plus, there is also the case that we don't observe anything from the past, but we can have, let's say, a new value, epsilon t, with some additional probability. The sum of all probabilities is 1. So this is, let's say, the model for the univariate case, and this is the model that can be described without necessarily using the thinning, but actually implying the thinning. So we can have, let's say, this representation here that says that we do have, let's say, observations zt, and zt are the ordinal random variables. We have also innovations epsilon t with some marginal probability distribution P of E, and we do have a random mixture through this Bernoulli random variable. So my representation is that my current value zt is this alpha t here is a Bernoulli, so this is actually either 1 or 0. If it is 1, I observe the previous time point. If it is 0, I observe a new value. So this is the very simple model. You can see here what's going on. So for example, this is a plot with different values of alpha. And what we can see here is that as far the alpha is going close to 1, we see that we can have a persistent, let's say, behavior that we stay for a long time at the same level. While alpha is so small, we can move quite quickly between different values. Okay, so this is the model I would like to generalize. Just a quick note that a lot of the mechanism and a lot of the, let's say, the tools for the univariate time series are not easily applicable here. So, for example, if I want to measure the serial dependence, perhaps the classical Pearson autocorrelation is not a good idea. So perhaps I have, let's say, to use other measures like Kramer's V or even this particular Cohen's kappa for ordinal data. So it is an interesting and perhaps a lot of opportunities here. How can we measure the kind of autocorrelation when we have ordinal time series? I don't know how, if you are familiar, but Pearson correlation does not work very well if you have, let's say, ordinal data with few categories. That's why we can use a little of different measures. So I'm not going in very detail on that, but this is a nice and fruitful, let's say, area for research. So I am extending here the DAR model in the bivariate case. So actually we observe now two discrete value time series. They can be counts, binary, ordinal, or whatever, but actually I'm going to use it for the ordinal type of data. Each of the process is a univariate discrete autoregressive, but we will put some cross-correlation between those two. So if for the univariate I need, let's say, this mechanism here to create a kind of, let's say, autocorrelation, in the bivariate case, we are going to have two random mechanisms that are correlated in order to create and introduce the correlation between them. And the way that we are going to couple the two series is through a copula. So we are going, let's say, to introduce the dependence through a copula. Copulas are very powerful to incorporate dependence. So actually, we do have a lot of results. We have very nice results for continuous variables. There are very many results now for discrete or ordinal variables. So this is going to be my mechanism in order to introduce the correlation between the series. This is the representation of the model. So I'm using the Hadamard, the element-wise product. So actually, what I'm saying here, perhaps this is the easiest representation, is that I have two random variables, A1t and A2t. They are a bivariate Bernoulli case. And actually, with this, I decide whether I'm keeping the previous values or I'm going to new ones. So here, all the correlation, all the let's say, the structure comes from the fact that the innovation terms here, they are going to be correlated. And also, the Bernoulli random variables here, they are going to be correlated as well. So this is the idea. So here, this is, let's say, a more formal definition of this bivariate discrete autoregressive model. And actually, what we can have here is that while we have the marginal distribution for the innovations, we can have a joint distribution which is defined through a copula. C is whatever copula we like. Remember that for the discrete case, since now epsilon 1 and epsilon 2 are two ordinal random variables, we need to take finite differences. So we need to evaluate the copula at these particular time points in order to get a proper probability function. So this introduces correlation for the epsilon. And this is a kind of, this is an example with Frank copula. So actually, what is interesting here is that as the parameter alpha goes up to 30, you see that all the probability mass is almost in the diagonal, while if we are, let's say, close to zero, what we see is much far away from correlation. If we are in the negative side, we can see, let's say, negative correlation as well. Okay, this is the one, let's say, part of the model. The second part of the model has to do with the random mechanism. So here we have two Bernoulli random variables. And for those Bernoulli random variables, again, we assume a kind of correlation, again by using a copula. So we have another copula here, and the model is like that. So we have two Bernoullis and a copula. Of course, if we want, let's say, independence, we can assume that the copula parameter goes to zero, or let's say goes to independence. And this way we can have this model as well. Okay. This is a picture for bivariate, let's say, Bernoullis. Again, you can see that if I have a big positive parameter, I have everything in the diagonal. Otherwise, I have anything in the antidiagonal. If we have, let's say, zero correlation, actually I can have either something like a similar pattern. For all those pictures here, all the marginals for Z1T and Z2T, they are exactly the same. So I can have very flexible things about all that. Having said that, what is the next case? So actually, if I have observed ZT minus 1, in the next time point, if both alphas are 1, I stay at the same values. If the one is 1 and the other is 0, so those two cases, I just observe the previous values or an innovation. And of course, if they are both 0, I observe a new value. So this is, let's say, all the mechanism, the machinery I need here. About the properties, I will go a little quicker here. The stationary conditions hold as far as the phi's are between 0 and 1. Under stationarity independence, the marginal distribution of ZK is the same as the distribution of the innovations. This is not true, however, for the joint distribution. And this is true only if I have, let's say, this condition here. One restriction for my model is that it only captures non-negative serial dependence. So I have to discuss how we can incorporate negative correlation as well. And finally, as far as the estimation, we're going to use conditional log likelihood. And for conditional log likelihood, we need the conditional distribution here. So you see that the conditional distribution can be written as a mixture of 4 components, depending on the values of the two Bernoulli random variables. So this likelihood is relatively easy to estimate and work with. Okay. So I do have some simulation, but I will skip it for saving time. What is the message from my simulation is that we can estimate quite nicely what's going on. One thing that we need to take into account is about the copula parameters, because actually we have seen that for small sample sizes, the copula parameters can be quite high. And the reason is that, for example, if you don't observe some particular, let's say, pairs, then your value, your parameter value can go very large. Okay. Overall, for relatively moderate subsizes, we can have, let's say, very good estimates. We have applied this to some data from Slovakia and Czech Republic. So this is unemployment for the two states. It makes sense to correlate the two countries because they have a common borders, and perhaps for some of us that we are a little bit older, we can recall that they were jointly a one country some years ago. So what we have done here is that we have fitted this model to this two time series. And actually, we have fitted a series of different models. The first model is independent discrete autoregressive models. The second is that we have a BDAR model, but actually with uncommon random mechanism. So actually we don't have A1 and A2, but just A. We can have uncorrelated alphas, but correlated innovations. We can have correlated alphas and uncorrelated innovations. We can have also the wider model, the model that has every kind of cross-correlation. So this is the best model. This is, let's say, the full model. And of course, we have also a Frank copula. This is the main result. So judging from BIC, the best model is the number 2. So actually here, we don't have correlation between the Bernoullis. Actually, we do have one Bernoulli parameter. And we see that the models, they have, let's say, different number of parameters. This is model 5 is the full model. And then each model has much less structure. Model 1 is the simpler one, which just assumes independence. So we see that actually there is sufficient dependence in this model. This is the estimated model. So we have estimated a model based on this. And of course, the likelihood ratio test shows that we have a statistically significant difference between the model. That's why we have chosen model 5. Model 5 is the model with every kind of, let's say, structure. Look at this parameter here. This is highly significant, but actually this is the dependence between the Bernoullis, and my parameter estimator is quite high. So this is, let's say, the kind of joint distributions that the model shows. You see that we do have quite large cross correlation, which actually expected because of the data and what we have seen. One important thing here is about forecasting. So for forecasting, we can use, let's say, the one step ahead conditional distribution. However, for larger, let's say, time points ahead, this is not any more easy to calculate. That's why here we have used a kind of simulation procedure that actually we simulated the values from the conditional distribution for a big number of times, and this can give us, let's say, the predictive distributions for time 1 point ahead up to time 12 points ahead. So this is, remember that we have 4 states for Slovakia and 3 states for Czech Republic. That's why we are missing 4 here. And these are the one step ahead predictive distributions. So for lag 1, we may say that the mode of the conditional distribution is 2 for Slovakia and 1 for Czech Republic. And as time passes, we can see how this may change. Okay. So this is, let's say, the modular forecasts for the different values. So this is, let's say, just an order 1 model. We can, let's say, extend this to model of larger order. And we can have, let's say, a kind of a dithetic Bernoulli. So instead of using alpha, we can use 1 minus alpha, changing a little bit the structure in order to have a kind of negative correlation as well. And of course, if we don't consider Bernoullis, but a kind of multinomial random variables, we can have a multivariate discrete autoregressive model. I'm going to the second part. So as I promised, the idea is that we're going to work for multivariate ordinal models, but now it is not that easy to define the whole thing in the multivariate setting because we lack of tools to define such things that are easy to work with. So we observe now K ordinal time series. K must be, let's say, assume it is larger than 2. And we want to model together cross-correlation and autocorrelation. And it is not simple to define a multivariate model. That's why we are going to define a lot of bivariate models, and using what is called the pairwise composite likelihood, we are going to estimate the models. So this is our strategy here. Just for completeness, there is very few literature on multivariate ordinal time series. Mostly there are models for longitudinal data, so actually we don't have large time series. And again, the one kind of models is based on a kind of multivariate mixed models. So actually we have a kind of probit ordinal model, or we can have, let's say, a kind of random effects model. So there is quite a few papers on trying to do something like that. Here, what we are going to do is that we have bivariate models, and actually we assume that the bivariate models are the marginal models from a multivariate one. So instead of having something in dimension, say, 5, we define all the combinations every 2 time series at order 2. So this is going to define a lot of models. And by something like that, this is, let's say, our model. So now I switch from the thinning type of models to the GLM type of models, because what I have here is that I have a multinomial distribution, and the probabilities, and especially the logit of those, they have been defined using the previous observed values. So ZKT is for the kth time series at time t. So the previous values, they are used in order to accommodate the time series effects. So this is my model right now. And of course, for each bivariate model, I couple them with a copula for this example, we can have, for example, any kind of copula. Here we are using a Gamble copula, and this is going to match together the series. Again, as we have done, we can calculate the bivariate, let's say, conditional distribution, and we can define, let's say, the log likelihood. And of course, this is, let's say, the full likelihood at this time point. What we are going to use is this idea of composite likelihood. So the idea is that it is not easy, let's say, to extend to the k-variate case. That's why we are going to use lower dimensional likelihoods, and typically we can have, let's say, this idea in the pairwise level. So composite likelihood is an inference function derived by multiplying component likelihoods of lower order, and this is how it works. In a generic definition, we can define the composite likelihood as the product of lower likelihoods, and the events here can be any conditional or marginal events. So this way we can have a lot of flexibility on that. This is, for example, the pairwise likelihood. So here, instead of using everything, jointly together, what we are using is a k-dimensional vector, and we specify all the k times 2 bivariate models. So my likelihood is going to have all those big terms here. Instead of a multivariate term here, we have the product of all bivariate terms. And this way, we don't need to specify the model in the multivariate case, but we need to specify the model up to the bivariate case. That's the good thing. The pairwise likelihood is doable, but perhaps is not that easy to maximize. So we are using here an alternative approach, and this says that maximize each pair separately and then combine the parameters in order to get your estimates. So what we are saying here is that we can define all the k times 2 bivariate log likelihoods. We maximize them and we estimate parameters, and then using some theory, we can combine all the estimated parameters to fix the parameter estimates. Just a very simplistic example for your convenience, what I'm proposing here is the following. Let's say that we have a trivariate Gaussian model with some mean vector mu and some covariance metrics. So you see here that I assume that I want to estimate the different means, mu1, mu2, mu3, the different variances, but I have a common covariance term. So if I take the bivariate margins, x1 and x2, I can estimate mu1, mu2, the two variances, and also rho. But if I take the pair x1, x3, I still estimate those parameters. If I take x2 and x3, I can estimate those parameters. So here I fit only bivariate models. What is the price here to pay is that actually I have 3 different estimators for rho hat. So actually I need to synthesize by using, for example, a kind of averaging those rows. See also that mu1 is estimated twice, mu2 is estimated twice. So for each parameter, I don't have just one estimate, but I have to synthesize by using the different parameters. That's the idea in this work. There is some literature on that. So actually, in this paper, Huey et al. In JASA, they are saying that if you maximize a weighted least squares criterion, so here what we try is to synthesize our estimators. This eta here is the negative Hessian matrix. So actually this way we're weighting the estimates by using the standard errors. And by using something like that, we can have a weighted mean estimator weighted with respect to the errors. So here, for each pair, we have an estimator, but also we have a standard error for that, taken from the Hessian. That's why we can, let's say, use the weighted mean in order to get our estimates here. So you see, I never maximize something more than a bivariate likelihood, and that's the idea. So for our model, assume that we have k ordinal time series, and we can have, let's say, up to decay levels. And my model is something like that. I do have, let's say, the probabilities, and then each logit of the probability is defined through the previous time points. So here is a model of order P, but of course we are going to work with order 1, and this is how we are going, let's say, to define the model. The bivariate model just uses 2 of the series, so we are going to define all the k times 2 bivariate models, and we have a joint distribution which is defined through a copula. So this is a different bivariate model than the bivariate discrete autoregressive that I have defined some times ago. Okay, and this is the pairwise likelihood, so actually we can also maximize this directly, so this has all the terms together. Okay. We have done a lot of work on the properties of this estimator. We know that it behaves very well. One big question is whether we have to use the simple average or the weighted mean averaging. We see from the results that they are giving quite the same results, so there is not a big deal if we weight or not, but perhaps this is due to the fact that we have a rather simple model with respect to the parameters. We also see a very natural behavior with respect, let's say, to the mean square error that goes very quickly to very small values. So actually, it seems that our estimators are behaving quite well. Just to have an idea, here we are using data from 6 countries. We have used much higher dimensions, to be honest. It is still doable, but just for illustration purposes, we're working with 6 in this example. So we have selected 6 countries and the unemployment rate. We have discretized the unemployment rate by using the quantiles of the data, and the data looks like that. So we see a little of different patterns, but for some countries you see, for example, in Finland we have a very quickly changing pattern. In Greece we have, let's say, quite stable for some period. The same for Spain, and we will try to fit the models. If we see autocorrelation, this is based on Kedal tau because we have ordinal data. So you see here that this is the correlation of Portugal at Portugal with the previous time point. So in the diagonal you see that we have a lot of autocorrelation. The only country without a lot of correlation is Finland, but that's why, because Finland moves quite quickly between the different levels, that's why you don't see a lot of autocorrelation. So this term here says the correlation of Portugal with Slovakia with lag 1. So actually here we see cross autocorrelations, cross correlation functions as well. The cross correlation at point 0 is this one. So you see that for some countries we do have quite a lot. So for example, Portugal is highly correlated with Spain, which is something that we would expect. And you see a lot of correlation between Italy and Greece, Spain and Greece, and things like that. So actually we do have a lot of interesting structure here. Our model is that. Our model assumes a multinomial, let's say, a mixing distribution here. Actually, what we observe depends on the previous time points for all the countries, and this is for all the models from K1 to 6. We have observed 104 observations for the time period that we're working with. So here are my results. Remember that I have ordinal variables with 4 levels, so we need to estimate 3 parameters. So this is, let's say, the ordinal levels for the variables and for the innovation terms. And here we have, let's say, the autocorrelation parameters from the different models. I have also the standard errors. So you see that some of the parameters are highly significant. I don't have estimators here because for some countries I have not observed all the different levels. And these are the final estimates using the trick that I mentioned. This is simple mean, this is the weighted mean. So perhaps if I play a little bit, you see very little difference between mean and weighted mean. Actually, this verifies what we have seen, that weighted mean has very slightly better results than the simple mean. And also, these are the parameter estimators for the copula parameters. For some countries, we do have very important cross correlation. I mean that the copula parameters are positive. What is very interesting with this approach, and this is, let's say, a very nice point, is that forecasting is not easy, because we can have, for example, if we fit for a particular time series all the bivariate models, we have a lot of different forecasts. So we need to synthesize the forecasts, and actually we need this way to derive the forecasting distribution. We have two different ways. The first one is to average the forecasting probabilities from each of the bivariate models, and then based on that we select the median or the mode. And the other one is to take one forecast from each model and then use a majority rule to define what's going on. If we want, let's say, larger lags, we can still use Monte Carlo in order to have the results we need. So here is a forecasting based on, let's say, the first approach, averaging the probabilities. So these are the one step ahead forecasting probabilities for the three first series. And you see how this changes across time. So we have up to 12 lags ahead forecasting. This is based on 10,000 simulations, and based on that, we can select what is the forecasting value if we must. This is, let's say, for the first three countries. This is for the rest of the countries. So you see, for example, that here is Greece, that we forecast that it is highly probable that we're going to have numbers at the very edge, I mean, in the highest level possible. Finally, there is a little more work on that, in the sense that if we have a lot of time series, we are going to estimate a lot of parameters. So if in our criterion we impose a kind of a sparsity penalty, so here we can have a Lasso type penalty for sparse estimators, we can, let's say, make zero shrink some of the parameters in order to have a better structure. So this is something that we have also worked, and actually this way, for the high dimensional case, we can have better estimators. One nice message here is that perhaps you may have noticed that fitting this stuff here is a two-step procedure. So actually you fit the bivariate models, and then taking the output, the estimators, you do this lasso trick. So actually this is a least square problem, and actually you can use even GLMNet in R in order to fit this second part of the model. So applying this lasso penalty is not difficult at all. Having said that, I have to wrap up. This is, let's say, a first attempt to fit multivariate ordinal models. There are interesting things about model selection. One may notice that this procedure is also possible for mixed mode data. So here I'm working only for ordinal data, but perhaps one can define different modes. You can have a continuous random variable and a count random variable, an ordinal random variable, or everything together. As far as we can define bivariate models, the approach is applicable, and you can have interesting results. One point that we are also considering here, and I didn't mention a lot, has to do with the fact that actually we need to define appropriate measures about how we measure autocorrelation and cross-correlation here, because especially if you have mixed mode data, it is not anymore that easy to define the cross-correlation terms. Finally, especially for the example that I have shown you about the rating of different countries, we would like to be able to cluster the different time series. So actually not only just modeling, but we would like to be able to define a model-based clustering based on the ordinal time series models for doing the job. I have a lot of literature here, everything that I mentioned, and thank you very much. I think that this is quite an interesting, let's say, topic for research, and I would be very glad to answer questions and, let's say, have ideas for further research and collaboration. Thank you very much.